is the fourth video for IB Physics Astrophysics unit, and we're going to be talking about relative and absolute magnitudes. Now, this is not quite as interesting as the life and death of stars, but it's something you need to know, and it really isn't that difficult as long as you like logarithms. Essentially what apparent magnitude is a relative scale of brightness. Basically, if a star has a small magnitude, then it appears very bright. Small magnitude is a star that appears very bright, and a large magnitude is a star that's very dim. So the brightest star in the night sky, which is Sirius, only visible in the winter though, has an apparent magnitude of roughly -1.5, which is very, very bright. Something like the moon, which is far brighter than any star in the sky, has an apparent magnitude of something like -6. The sun has an apparent magnitude of -27. And in general, the way it's defined is that a star of magnitude 1 is 100 times as bright as a star of magnitude 6. And magnitude 6 is kind of the limit as to what you can see without a telescope. And magnitude 1, there aren't very many stars that are brighter than that. Maybe 4 or 5 in the night sky that are brighter than magnitude 1. The unaided human eye can see stars up to about magnitude 6 on a dark, clear night, which we don't get very often in Tulsa. There's tons of light pollution. And because of this definition, that a star of magnitude 1 is 100 times as bright as a star of magnitude 6, what that means is that when you start at magnitude 1, you have to multiply by 2.512, or divide by 2.512 to get a star of magnitude 2. And to go from magnitude 2 to magnitude 3, you have to divide again by 2.512. And there's again a 2.512 ratio between magnitude 3 and 4, another 2.512 ratio between 4 and 5, and another 2.512 ratio between 5 and 6. So if we start with a brightness, or a magnitude 6 star, and go to magnitude 5, we have to multiply by 2.5 on the brightness. To go from 5 to 4, we have to multiply the brightness by 2.5 again. And so we multiply by 2.5 5 times. And the reason that value 2.512 is chosen is it just so happens that 2.512 raised to the 5th power is 100. And the mathematical relationship is b1 over b2 equals 2.512 to the raised to the power m2 minus m1. Now, there are two different stars here. b1 and b2 are the brightnesses of those two stars, and m2 and m1 are their apparent magnitudes. You do not need to derive that equation. You don't even need to memorize it because it's found in your equation sheet, but you do need to know what everything stands for because the equation sheet doesn't tell you that. Now, an example of how you use that, Sirius, which is the brightest star in the sky, has an apparent magnitude of -1.47, and Vega, which is also a very bright star, has a magnitude of 0.04. The question is, how much brighter is Sirius than Vega? So what you have to do, you use that equation. You say the brightness of Sirius divided by the brightness of Vega equals 2.512 times the magnitude of Vega minus the magnitude of Sirius, which is 2.512 raised to the 0.04 minus -1.47 magnitude. And so we get brightness, the ratio brightness of Sirius to the brightness of Vega equals 4.02, and so Sirius is about 4 times as bright as Vega. Notice this doesn't tell us the brightness of either star, it just tells us the ratio. So that's what magnitude does, is it relates to the ratio, and it's a logarithmic scale. So a star, the difference in brightness between a star of magnitude 1 and a star of magnitude 2 has the same ratio as the brightness of a star of magnitude 5 to a star of magnitude 6, but the ratios are the same, not the arithmetical difference. The other thing you need to know about is something called absolute magnitude. Relative magnitude is a scale of brightness. Absolute magnitude, on the other hand, is a measure of luminosity. And the way we define it is that the absolute magnitude of a star is what the apparent magnitude would be if it were 10 parsecs away. Now 10 parsecs, remember, is about 32.6 light years. So it's a long way away. And so what we say is that the brightness as seen from Earth and then B10 is the brightness as seen from 10 parsecs, is equal to 2.512 times the ratio of the apparent magnitude at 10 parsecs, capital M, minus the apparent magnitude from Earth. And so we have to do a little bit of work. I hope you like logarithms. But one thing we can say is that, well, remember the definition of brightness? It's luminosity over 4 pi d squared, where d is the distance. So L over 4 pi d squared is the brightness on Earth, whereas the brightness at 10 parsecs is L over 4 pi times 10 squared. And that equals 2.512 raised to that power. Now we can cancel out a lot of stuff here, and what we get is 10 over d, quantity squared, equals 2.512 raised to that power. Then you take the logarithm of both sides, and we're going to take the base 10 logarithm, not the natural log. So it'll be log, or 2 times the log of 10 over d equals m minus m times the log 2.512. Now that logarithm works out to about 0.4. And so we can say that m minus m equals 5 log 10 over d, or negative 5 times the log of d over 10. You add the apparent magnitude to both sides, and you get that formula, which is given to you in your equation sheet. Again, you don't need to memorize it. You probably don't even need to know the derivation, but you do need to know what everything stands for. Remember that this is a log base 10, not the natural log. Figure out where that is on your calculator. And d has to be measured in parsecs. If you're given d in light years, you have to convert. A few things about absolute magnitude. It tells you luminosity. The sun, while it is very bright because it is very close to us. Its apparent magnitude is something like negative 27. However, it's not particularly luminous by the standards of stars. If the sun were 10 parsecs away, which is not that far in astronomical distances, its magnitude would be about 4.83, so its absolute magnitude is 4.83. So it's not a very luminous star, but it is very bright because it's very close. On the other hand, there are some objects out there called quasars that are very, very far away, but incredibly luminous. They have an apparent magnitude of usually somewhere on the order of 14 to 16, which you need a rather large telescope to see. But because they're so far away, their absolute magnitude is generally between negative 20 and negative 30, which means that if one of these quasars were 30 light years away, it would appear as bright in the sky as the sun is. So think about that for a second. And now we're going to do an example. You've got some star. We know that it's 35 light years from Earth. Don't ask me yet how we know that. We'll find that out later. And it has an apparent magnitude of 2.4, so middling brightness. We want to find its absolute magnitude. So we're going to use the equation absolute magnitude equals the apparent magnitude minus 5 times the log of d over 10. But remember, d needs to be in parsecs, so we got to convert from light years by dividing by 3.26. which means that the distance is 1.07. No. Did that wrong. Calculator entry. 10.7 parsecs. So we have 10.7 over 10. And when we do this, we get an absolute magnitude of 2.25. So this is more luminous than the sun by roughly a factor of 6. No, more than that. 8. I'll let you figure out how I got that later. And that actually brings us to the end of this particular video. You should be able to explain what is meant by absolute and relative magnitude. You should be able to apply those equations. And you should ideally be able to derive the one for absolute magnitude, although they probably won't ask you to do that on the test.